In this video, we're going to show how to visualize hidden layers of a convolutional neural network, the same network that we used in the previous video to detect cats and dogs in images. We're going to use two different strategies. One of them is using the outputs of the hidden layers, and the other one is using gradients. Gradients is basically the rate of change, multi-change according to one input or more. We're gonna show first the approach of the outputs. So we're gonna use the same model. We're gonna load the model that we trained in the previous video. In the previous video, we saved it in this file, so we are loading it. And here's the summary. You have a interleaved convolutional and max pooling layers, followed by a flattening, and then dropout regularization and this layer. But in this video, we only care about the first 8. 1, 2, 3, 4, 5, 6, 7, 8. And we're gonna create another model that is exactly the same, makes reference to the first, but it's gonna have 8 outputs, one for each of these convolutional layers and max pooling layers. Okay, so let's use image first. In order to get the output, we're gonna feed each the new network with an input, which is the same image. So to test it, we're gonna load an image of a cat from the same folder that we used before, and then we're gonna rescale it because neural network takes value 0 and 1, no, not 255. Unsigned integer doesn't take it, and then we're gonna add a unitary dimension for compatibility, and here's the cat. Okay, now let's create the model. Okay, so the model that we loaded, we're gonna take the first 8. This is saying we're going from 0 to 7, the first 8 layers, and we're gonna iterate through them. For each layer, we're gonna get the output, and we're gonna concatenate those outputs into an array using these brackets. So we have a vector of outputs here, and now we're gonna use a new overloaded method of model to create a model using the model input, which is the same input as the original model, and the outputs. So you can see this as tensor references, tensor graph references, and this is going to create a new activation model. Okay, so let's create the model, and now we're going to feed that model with the input image of the cat and get the output value, which is size of 8. Unsurprisingly, because we're picking 8 layers, so we have 8 outputs. Okay, now let's take a look at the summary of the model, which is as expected. We have the 8 layers that we selected, and the input is the input image, the input model input layer that we added because of this. Okay, so now let's analyze the first layer. Activation. This is the outputs of the new model. So we're gonna take the first layer, and the output is 148 by 148. Unsurprisingly, the output of the first layer with 32 features. Okay, so let's see how it looks. Let's use pyplot, and let's take a feature number 31. And this is always 0 because there's only one sample in these experiments. And use this using this color map and using pyplot. Okay, so notice that in the first layer, at least this feature in particular is behaving like a Sobel filter or something like that. As mentioned before, the first layers in a convolutional neural network behave something similar to image processing functions like filters, Gaussian filters, Sobel edge detector, erode, delayed, things like that. You can expect things like that transformation at the beginning, so this is not surprising. Let's take a look at other layers. Yeah, there's some color transformation in there. Okay, and 31 is the last one. You can also see it this way. -1 means the last value in that dimension, which is the same as 31. Okay. Okay, now let's take a look at another one, number 17. It looks like this. It looks like it's focusing on the eyes. Okay, now let's look at all of them together in a tabular way. So I'm not gonna go in details to the script that does this. You can pause it here to take a better look. I just gonna explain briefly. So we're gonna go through all the layers, the same first 8 layers of the original model, and get the names of the layers. And then we're gonna zip the layer names along with the activations, which is the outputs of the new network, and that's basically gonna interleave to make pairs. The first goes with the first, second with second, third with third, and so on. So for each pair of layer name and the activation, what we're gonna do is gonna put it in a grid like this. So we need to know the number of features for a particular layer because each layer has different features. As you saw, it could be 64, 120 something, and 256, things like that. It varies from layer to layer. So that's why, and the number of features is the last dimension. So that's why we put -1 in here to get the features, the number of features. And Python is zero index, so 1 means the second. So this is 0, 1, 2, 3, so we take the second one. Since the image is rectangular, we just only need to pick the first one. And from that, we're gonna basically calculate how we're gonna distribute it. We create a zero matrix, the display grid, in which we're gonna place the image, the output image. So here we take the layer activation, which is the current layer output, the current output of the layer. This is only one sample, so we take 0, we take the whole image, and we take the current feature, and that's gonna give us the image. And then for aiding visualization, we're gonna subtract the mean and also divide by the standard deviation, and also resize the values from 0 to 255 and cast it to unsigned integer 8 so that it can be visible. And then after we have the grid finished, we just display it, and we can see it in here. Okay, let's run it. Okay, so now you can see that the closer the closer the layers are from the input, the more similar it's going to be from the input. The closer are the layers from the output, they are going to be more similar to output. So you can see that you can expect that the outputs of the layers, the first layers, are more general and more easily more visual, more similar to the image, and the later layers, the backend layers, are going to be more encoded. And you can see it in here. The first two layers are similar to the cat, and then the third and fourth, you're gonna see more edge detection. You're gonna start seeing more the eyes, the ears of the cat, and as we go on, there's more patterns, and eventually it's gonna be very encoded, so it's not understandable after a certain point. Okay, so we show how the outputs of the hidden layers of the convolutional network looks, but to understand, to have an intuition of what each layer is doing, we're gonna use the gradients, and then we're gonna use something like a stochastic gradient descent to with the input image, basically, but instead of being descent, it's gonna be ascent, to visualize what is more important for the particular layer. So let's go to it. So instead of using the model that we trained before, we're just gonna use the BGG16 model, pre-trained model. Okay, since we want to compute the gradient is computed in terms of TensorFlow graph, and for that we need the graph. If we have the eager execution mode, instead of having the graph is going to be just computed into a number and we lose the graph. So we have to execute this in order to have the graph and avoid crashing a TensorFlow to crash. Okay, so we just run it. Let's create the model using the ImageNet dataset. And the summary, we are already familiar with this. It has more convolution layers per max pooling than the other one, and also more layers. Okay, so let's compute the gradient for one of the layers. Let's pick up one in the middle, this one. Okay, and feature number 0. Okay, and now let's take the layer by name get the output, which is a graph, and get that feature in particular, and then get the average, the mean, and that's going to be a scalar. But this is not going to be a value. This is going to be like a, visualize this like a graph. So the mean is the last node in the graph, and the input node, the child node, or the parent node, depending on how you see it, is going to be the layer output. And the layer output is just another graph. So nothing is computed at this point. We just have a graph representing the loss, which is the mean of the output of the layer. Okay. And from that, we're going to compute the gradient. So that loss, this graph, we're going to compute the rate of change, the multidimensional rate of change, according from that output according to the input. So this is like calculus. This is like the derivative of y according to x. So this is y and this is x. So it's going to compute you symbolically the gradient as a graph. Okay, let's run it. And now to smooth out the output, we're going to use the L-square normalization, which is basically the square root of the average of the squares of the values of the tensor. So here's the square of the values of the tensor. We take the average, the mean, and then we take the square root, and then divide each of the gradient values by this. And to avoid zero division, we add a small value here. Okay. Now we have the graph representing the gradient, and we want to compute the actual gradient values. And to do that, we create a function on the fly. So this function is going to take as input the same input as the original model, and the outputs are going to be the loss and the gradient. So these are graphs, symbolic graphs, and these are going to be the outputs. So a function is going to be created for this. Okay, now let's just feed it a tensor, an input tensor, which is the same size of what will be an input image. So this is going to be 0. Let's run it. The loss, of course, is 0. The gradient shape is the same as the input. Okay, so now let's compute this for all the layers. I mean, for a few layers, but okay, I'm just going to skip through this because I'm going to show in more detail. This is going to be the same as the other one, so I'm not going to go through it. Okay, in order to visualize the image, again, you have to, I mean, it's not the same how what the network sees is not the same as what we can see, so we have to convert from what the network sees to what we can visually understand. And for that, we subtract the mean, we divide by standard deviation, we convert the values from 0 to 1 to 0 and 255 and convert it to sine integer 8. So that's going to be a function that we're going to use. Okay, now we're going to create another function to use the gradients. The input is going to be a layer name, the channel or the feature, and by default it's going to be size of 150 because we know the image is 150 by 150. Okay, so let's get the layer name, the output. Let's compute the average again through all the tensor values and the given feature. So this is going to be a scalar. And now let's compute the gradient of that scalar output symbolic graph according to the model input. Again, we have the gradient. We do again L-square normalization and create the dynamic function by using the model input, the loss, and the gradient. And now that we have the function to compute the gradient, we're going to do something like stochastic gradient descent, but instead of being descent, it's going to be ascent. So let's create an input image, which is going to be like a random image. And that image, we're going to feed it to the function. So it's going to give you the value of the loss of the layer that we are analyzing, the layer and feature, and also the gradient value. And the gradient value given a step, which is something like the learning rate, which is 1, is going to be added into the image data. The gradient value is the same size, the same shape as the image data. So that's why you can add it like this. And then eventually, once you accumulate all the gradients after 40 steps, we're going to return it. And yeah, we're just going to call this function. And this should show it in a moment. Yeah. So the output is going to be something like a dot pattern. So let's do it for all the layers. So here's a generic function where you specify a layer name, you create some grid like we used before for the results, and you just call the the function that we created above for the layer and the feature, and we iterate through all the feature and put it into a tabular way. So I'm going to show you the results of that. So okay, so let's say for this is block 3 conv1, the one that we saw, this is the blue one. This is this in particular is the one that we just saw now, the dot pattern. So notice that layers have a different amount of features. Some have a maximum 512, but to make this simple, let's only see the first 64 of each layer. So we're gonna put this into a matrix of 8 by 8, 64 squares. So we're gonna call that generate function that we just saw on each of these or the first 64 features, and yeah, and visualize it like this. Okay, let's get first to this layer, then to this one, then to this one, then to this one. So for the first one, you can see like there's some diagonal patterns, there's some color patterns, and some horizontal, some vertical. So maybe this could be visualized something like a Fourier decomposition, in which, for example, Fourier transform decomposes a signal into sines and different sines of cosines of different frequencies. This is maybe this decomposing the image. It can be seen also like image processing filters, as mentioned before. Okay, the second layer, this layer, this layer over here has more texture-like patterns. And then once you go to the later layers, you might see some complicated patterns like eyes, ears, and things like that. Okay, now let's show another way of visualizing the output. Now we're going to use the same model, the VGG16, and we're going to show it through a heat map. That is, we're going to superimpose the output of the hidden layer using the gradients into the original image to see what is the most important thing that make it to take the decision to choose one thing or the other. So we're gonna create a VGG16 model that is a generic model to detect objects in images. We are familiar with this already. Okay, so again, this is a summary. Okay, again, we're gonna disable eager execution because we're gonna use gradients. These are we're gonna use the pre-process input. We're gonna load an image of an elephant, of an African elephant, and we're gonna pre-process it using the pre-process input from the VG16 library, which is good. We don't have to do it as we did before. We're gonna convert it into an array, NumPy array. We're gonna add a unitary dimension at the beginning for compatibility. We're gonna pre-process it, and now we have the image, and we don't feed it to the model. Notice that we did not do anything in the model. We just loaded. So this is ready to predict the category on the image. Okay. Okay, so the shape is 1000. I don't know what is 1000. I don't know if it has a maximum 1000 categories or just pick up the 1000 best. But it also has there's a decode predictions that helps decoding the output of the model. So we're gonna use it, and let's run it, and you can see that we're gonna pick the top 3, and this is the output of prediction. So we see that the African elephant has around 84% of probability, followed by Tusker and Indian elephant with low probability. And if you use from the predictions, you get the maximum. With the maximum probability, you're gonna get 386. You can see that this is one of the 1000 categories here. So that corresponds to African elephant. So that's it's basically the model is predicting that is an African elephant. Okay, so now we want to know why it is predicting an African elephant. So for that, we're gonna get the output the output corresponding to the African elephant, which is 386. So now I'm getting here the symbolic graph for that particular output, and we're going to do a gradient on it. Okay, and we want to know what happens in the block in the last layer. What is the output of the last layer? And this is what we're going to visualize. The block 5.3 is this one. This is the last convolutional layer. So that's what we're going to visualize. Okay, now, yeah, this will give us the graph. And of course, it's 14 by 14 by 512, which is this one. This is the number of features, the output of that last layer. Okay, now we're going to compute the gradient of the output that we got in here, the output of the African elephant category, and corresponding to the last layer output. So the gradient is not going to be like in the last example, it's not going to be relative to the input, but it's going to be relative to the last layer. And the output of the gradient, of course, is the same size as the input, which in this case is the last hidden layer of convolutional neural network. And for that, we're gonna for the gradient, we're gonna compute the mean, the average of the first 3 dimensions. So we have a first dimension, which is sample, only one for this type for the experiments, and the image dimensions, we're gonna just average them. So the output is gonna be 512, which is the number of features. So this is still a symbolic graph. It's not computed yet. So that's the output size, 512 elements. And now we're going to create the function to compute the gradient. Notice that it's using the backend library to create this function. That this K library is the backend library from Keras. This is the one that is used to create compute the gradient, and also to create these dynamic functions to calculate the gradients actual values. So the input is again the image of the elephant, and the outputs are going to be the gradients computed in here. Is going to be the first output, and the output of the last layer. Yeah. Okay, so let's create the function and just give it the elephant. When we give the elephant, the output, of course, is the same size of the last hidden layer that we chose, and the output of the gradient is going to be 512 because we're computing the gradient for each of the features. Okay, so what we're going to do to visualize this is we are going to transform the output value of the hidden layer by multiplying each of the features of the hidden layer by the corresponding gradient. So we're going to iterate through all the features, multiply the gradient by. So it's like we have a small sub image that was 14 by 14, and we're going to go through the 512 and multiply by the corresponding gradient. And with that, we're going to have the average of all the features. So now we take away with that average in the last dimension, which corresponds to the feature 512 features. Basically, we are getting rid of that dimension, and now we're left with a heat map which is of size 14 by 14. And now we're going to do some transformation here to visualize it using a pyplot. Okay, so that's how it looks. But now we're gonna put this on top of the elephant image. So I'm not gonna do it here because I don't have OpenCV support, but this is the code that is used. So in OpenCV, you resize that heat map that I just showed. This heat map here, 14 by 14, is gonna be resized to the size of the elephant image, and then it's gonna be applied on top of it, and you can see it in here. So we can see the red is the most important part. And so you can see from here that the ear, the face, and the nose of the elephant were determinant factor to saying that this image has an African elephant in it. Okay, that's it. Thank you for watching.